Let's have a look at another question. So here we are dealing with circuits. A student performs an experiment to determine the EMF epsilon and internal resistance R of a given battery. The student connects the battery in series to a variable resistance capital R with a voltmeter across the variable resistor as shown in the figure above, and measures the voltmeter reading V as a function of resistance R. The data is shown in the figure given below. Now, we have the capital R readings, the voltage V readings across this capital R. We have current I readings, obviously, and we also have 1 by V readings. Derive an expression for the measured voltage V in terms of capital R, epsilon, small r, the internal resistance, and other physical constants, if and when necessary. We can use KCL and KVL for this. We can assume that the current flowing in the entire circuit is I. There is no need to use KCL further because there is just one single loop. We will try to use KVL. KVL, we can start from the top left of the equation. We will assume polarities to all devices used here. So we get the, starting from the top left, going clockwise, we get the equation plus IR minus epsilon plus I into small r is equivalent to 0. Rewriting the equation, you get epsilon is equal to I into small r plus capital R. I know that this voltmeter measures the potential difference across capital R. Since the potential difference across capital R is nothing but IR, we also have V is equal to I into capital R. Combining this in the above equation, we get EMF epsilon is equal to I into capital R, which is V, plus I into small r. Now, we have an equation for epsilon as I into capital R plus small r. We will just substitute that here. We get V is equal to epsilon minus I into small r. Now, inside this particular equation, I know that I can write I as E by R plus R. So this becomes epsilon minus epsilon divided by small r plus capital R into small r. If I take epsilon common, I get epsilon into 1 minus r by r plus r. This can also be further rewritten as 1 can be written as r plus r divided by r plus r. And when you minus the r, you are left with capital R into, or I can write capital R outside, capital R into 1 by r plus capital R. The problem with this expression is, while this expression is correct, it is no way close to the equation of a straight line. So we will take the reciprocal. We get 1 by V is equal to 1 by epsilon into 1 by capital R into small r plus capital R. This can be further rewritten as R divided by epsilon into 1 by R plus R and R cancel on the second hand side, leaving us with the expression 1 by epsilon. This equation resembles that of a straight line. Y is equal to mx plus b or c, depending on the curriculum you study under. Now, rewrite the equation in terms of 1 by v as a function of 1 by r. Done. On the grid below, plot the data points for a graph of 1 by v as a function of 1 by r. Here the y coordinate is nothing but 1 by v. The x coordinate is nothing but 1 by r. The expression is y equal to mx plus b. 1 by v is equal to r by epsilon into 1 by r plus 1. Sorry, Yes, R by epsilon into 1 by R plus 1 by epsilon. If I plot the points and join them, the equation is almost and should almost represent a straight line, with the line of best fit being drawn as shown. Moving on to the next part. Use the straight line to obtain the values of the following, that is epsilon and R. Epsilon you can find out from the value B. Here B is nothing but, in an equation y is equal to mx plus b, mx plus b. M stands for the slope, which can be found out as y2 minus y1 divided by x2 minus x1. B is nothing but the y-intercept 0, b. Extending the line backwards, the b-intercept can be found out. And since b is nothing but 1 by epsilon, epsilon value can be found out by finding the value of b to be approximately 12.5 volt. R value can be found out by finding M. Since M is nothing but R divided by the epsilon, and M is found from the graph to be approximately 0.0463 as given in the scoring guidelines. We already know the value of EMF is 12.5. You can use that to find the value of R as 0.58 ohm. So here are the values of epsilon and R found out from the graph. You do not have to get these exact values. You can get an approximation, and there is scope for error provided this is a line of best fit. Moving on to the next part. Use the results from the experiment to calculate maximum current that any battery from can provide. I know that I can find current epsilon EMF as I into small r. This is the condition for the maximum current to be produced. And since epsilon and R are known, I can divide them by each other and rewrite the equation as I is equal to epsilon divided by R. Epsilon is approximately 12.5 volt. R is approximately 0.58, giving me the value of I as approximately 21.6 ampere. Moving on to the next part. A voltmeter is used to determine the EMF of the battery after removing the battery from the circuit. Two voltmeters are available to take this measurement. One with a low internal resistance, one with a high internal resistance. Indicate which voltmeter will provide the most accurate measurement. The voltmeter with a higher resistance will provide a more accurate measurement, since a voltmeter is a device that is connected parallel to another device, whether active or passive, whose voltage you need to measure and record. And so if a voltmeter has a high resistance, that means the current that actually passes through the voltmeter will be minimal, while the current that passes through the actual device will be as maximum as possible, which is what we need to get a more accurate measurement of voltage across the device, whose voltage we're trying to measure. This concludes the answer to the question.